So let's move to the PLS first. And in this, you can see the option called discriminant validity. So discriminant validity is coming here. Okay. So when you go to the discriminant validity, if you click on the discriminant validity, two criteria. One criteria is for null lurker, and second criteria is HTMT and close loadings. So there are three criteria you can see. Let's say first criteria. In for null lurker criteria, you can see it is a for null lurker criteria. The first value is called square root of the AVE, and it should be greater than all other. 0.749 should be greater than 0.692, yes. Greater than 0.723, yes. 0.7, yes. 0.68, yes. Then 0.783 should be greater than 0.683, yes. Yes, yes. 0.783 is greater than 697, yes. Yes. Okay. So we can see that our criteria is fulfilled. Now we are moving to the hetero trait and mono trait. All the values are less than 0.8, so no problem. If any of the value is more than, so we are not comparing here one value with another value. We are comparing all the values with a single value that is called 0.8. So all these values should be less than 0.8. If yes, it means you don't have any problem of discriminant validity in the scale. So in this way, we can check the discriminant validity in the model. And I'm showing you one thing that in the paper, how to report it. Okay. So normally the second section, whenever you write a paper, the first section in data, I'm talking about the data analysis part. In most of the papers, I have seen that in data analysis, the first portion is sample demographics. This is the way we write the sample demographic is this. The second section is liability and validity analysis. And this is the part we are discussing today. And I am just showing you the result, how we represent the result. In most of the papers, I have seen this table. So in one single table, the name of the construct is green procurement. These are the item code. And this is the factor loadings, construct loadings. All should be more than 0.7. 1 or 2 may be less than 0.7, but it is approaching the 0.7. Cronbach alpha should be greater than 0.7. But as I told you, the ideal range is 0.85 to 0.9. So you can see all the values in that range. Composite liability more than 0.7, AVE more than 0.5. So all the conditions of convergent validity fulfilled. So this is the format of representing the liability and validity in the table, in the paper. Similarly, the convergent validity you have to put like this. So this is a for null lurker criteria. And the first value is the square root of the AVE. And all other values are the square root of AVE. So in this way, we report the for null lurker criteria. HTMT ratio, you have to write like this. The same table, no change. You can cut and paste from the PLS to the paper. No change. Only thing we have to prove that the HTMT ratio should be less than 0.8. So the way we prove discriminant validity is this. So paper is already shared with you, so you can go through by format, which format we can use to represent the liability and validity. So I hope we have learned how to report the convergent validity and discriminant validity in the scale. So these are the conditions. So 3 conditions we have to check for convergent validity, and 2 conditions we checked for discriminant validity. So that is for null lurker, HTMT, and I hope now you are familiar with the for null lurker word and the HTMT ratio. So this is the 2 popular methods of testing the validity. So we have, so far we have discussed in the today, we have discussed the normality, we have discussed the reliability, Cronbach alpha, we have discussed the construct validity, all these things. Now we are moving to common method bias. But before moving to the common method bias, one thing I am going to include. So that is called multi-collinearity, because many questions are coming for multi-collinearity. So before going to the common method bias, I'm just adding a new slide. That is the multicollinearity. Because nowadays I have seen many people are asking about whether your data is suffering from multicollinearity problem or not. So today I'm showing you how we can check the multicollinearity and how we can correct it. Multicollinearity. So if you run the PLS, you are having an option called collinearity statistics. I hope you can see here below the discriminant validity, we are having a case called collinearity statistics. So if you go to the collinearity statistics, so the software is calculating collinearity statistics item wise. And the condition is that collinearity is measured by VIF. So let me write here. Number one, multicollinearity. Multicollinearity is measured by VIF. VIF stands for variance inflation factor. Variance inflation factor. Number two, VIF should be less than 3. So this is the conditions. And if you ask me what is multicollinearity, multicollinearity means very high correlation with other items. Very high correlation between items. So you have to prove also that your data must not have multicollinearity problem. And if VIF is more than 3 in any item, so I should write here VIF more than 3 in any item indicate redundancy and multicollinearity problem. So these are the things which you should aware about the multicollinearity. That multicollinearity, let me also copy here, copy from this and paste to the PPT. Similarly, this portion also and paste here so that I will convert it into lines. Okay. So we understand two things, that multicollinearity is measured by variance inflation factor. Number one, variance inflation factor should be more than 3, less than 3, and very high, it represents very high correlation between the items. And if VIF of any item is found to be more than 3, it represents the presence of redundancy or multicollinearity problem. So these concepts you should know. Okay, so let me share the PLS again. So where is PLS? Yeah. So I hope you can see the PLS. We clicked on multicollinearity, collinearity statistics. We have seen all these values. All these values are less than 3. So in this data set, we are not having the problem of multicollinearity. And now the question is that if suppose we are having the problem of multicollinearity, then what to do? Believe me, we have only one option: remove the items. In this case, we are having only one item, one choice: remove the items where VIF is more than 3. Otherwise, you have to do some change in the values of the data to remove it. So you have two options: either you remove the values, you remove the items with high multicollinearity, or change the values. Otherwise, we don't have any solution. So I also included the collinearity statistics in today's session. Nowadays, everybody is asking that. Now the next is, after multicollinearity, I will send you the modified slide. The next is biasness. How to measure the biasness? Although biasness is more related with Amos MO software. But nowadays, I found that even if you are applying PLS, you have to prove that your data is free from biasness. So there are many methods of biasness, measuring biasness. Two methods are very common. One is called Harman single factor method, and second method is known as common latent factor method. Latent factor method we can apply only in MO, so we can not covering here. Harman single factor method I am showing you. And still today, although there are many critics of Harman single factor method, they say that this is a very old method, why you are applying this old method. But still today, I have seen many A category papers where they are still following the Harman single factor method. Even A star paper also. So today I am going to show you how to check the biasness of the data. So for that, you need to open the SPSS. So I am going to open the SPSS software, take the data in SPSS, and will show you how we can calculate the measure of biasness by using Harman single factor method. So first of all, I will open the SPSS. SPSS is going to open. I will import the file and will apply the Harman single factor method. And the method is very easy. Within 2 minutes, you can do it. Okay. So this is SPSS. I hope you can see this SPSS file. I am going to import the data, CSV data. And this data we are having in workshop Smart PLS. So this is the data which we are using. So you can import the data directly. The software will import the data in 1 minute. Okay, so this is the data set. I am going to the analyze, dimension reduction factor, and I'm taking all the items including dependent and independent variables here in the left hand side. I'm going to the option extraction. Here I'm giving a condition that I want to extract only single factor. How many factors I need to extract? Only one. That's it. Just continue and okay. So you will get a table. This table name is total variance explained. The value you can see here, this value should be less than 50%. This value should be less than 50%. If it is less than 50%, it means your data is free from biasness. It means your data is free from biasness, and be happy. So this value should not be higher than 0.5. If it is higher than 0.5, then you are having a problem. If it is less than 0.5, no problem. So in this way, we can check the biasness in the data, biasness in the responses. Although this is the biasness of the questionnaire, because the name of the biasness is common method bias. It means your scale is having biasness or not. But we are measuring the biasness from the responses. So we are measuring the biasness from the responses, but we are proving that the scale is not biased. So that thing you should know. Okay, now I think biasness is clear. We again go back to the PPT. So common method bias, nowadays it is almost compulsory to prove that your scale is free from biasness, right? And the second biasness is, I have seen in many paper, I will also show you the where it is written. There is another biasness is called non-response bias. Non-response bias, that is called NRB. So what is NRB? Non-response bias. And somebody, sometime the reviewers ask you, just 1 minute, some people are asking me inner VIF or outer VIF. So we are talking about the inner VIF. Okay, outer VIF. Outer means VIF between the items. So both VIF values you have to check, inner VIF, outer VIF. And more, the most important VIF is inner VIF. So people are asking me in my chat box, I am talking about the VIF, which VIF, inner or outer. So more important is inner. Sorry, outer. And So you have to click on outer VIF. Inner VIF is talking about the inner model. And inner VIF is not a multi-collinearity because that is the correlation between the dependent and independent variable. So you have to take care of the outer VIF value. So I hope you are getting it. Right? Okay. So we are discussing the non-response bias. The non-response bias is the major problem of today's research. In India, when you send the questionnaire to other people to fill, the problem is that they are not ready to fill it. And why? Because frankly speaking, I myself feel very difficulty in filling the questionnaire. There are two problems. There are two problems in filling the questionnaire. Number one, I don't have time. Number two, I'm not getting what you're asking me. So whatever questions you are framing, I'm not clear about that. Number three, I do not want to share information with you. So there are many problems why people are not interested in giving me the data. So that is called non-response. That is known as non-response. So now the question is, the people who are not giving you response, suppose they give you response. If you are getting the response from the people which are not ready to give you response, do you think your result will change? जिन लोगों ने आपको रिस्पॉन्स नहीं दिया, अगर वो दे देते तो क्या आपका रिजल्ट चेंज होता? So the simple thing is that there are many people who are not ready to give you response. If suppose they give you the response, do you think your result will change? If yes, it means your data is suffering from non-response bias. So that is also a kind of biasness which reviewer can ask you to discuss. So I have seen in many papers, I will also show you that the authors mention the non-response bias. So they say that we divide the respondent into two categories: early respondent, late respondent. The early respondent are those people who gave us response without any effort. Late respondent are those people who initially declined to respond, but because we have to pursue many times, so after some time they become ready to give the response. So the early respondent are the normal people, normal respondent. The late respondent are non-respondent. Initially they denied, but because of the pursue, they're ready to give the response. So now we are finding whether the early respondent are different from the late respondent. So for that we applied paired sample t-test, independent sample t-test. Because early respondent and late respondent are two independent sample. So we try to find out the difference in the mean they are providing to us. Or we can apply the moderating effect, whether the type of respondent is having the moderation effect in the data or not. So anyhow you can represent that there is no difference between early respondent or late respondent to prove that your data is not suffering from non-response bias. So there are two types of biases I have seen in the paper. One is the common method bias, and second is the non-response bias. So I found that many times the scholars are not aware about these biases, so they don't know how to tackle them. But these two biases are very common, and slowly, I believe that the reviewer will ask you about these things. So I think this is about common method bias. The final concept which I am going to discuss today. So this is Herman single factor method. So how we applied, we have seen that in FA, and the variance explained should be less than 50%. This method is very old method, but still it is used by the authors. And the fifth concept that we are going to use in Smart PLS, this is called bootstrapping. From tomorrow, we will use this term again and again. Now, what is the bootstrapping? What is bootstrapping? Bootstrapping means suppose we are having the non-normal data. Bootstrapping is the solution of non-normal data, right? What is bootstrapping? It is a solution. Bootstrapping method is a solution to what? If your data is not normal. Bootstrapping makes your non-normal data into a normal data. So that is, this facility is available in PLS software, right? So let me try to explain what is the meaning of bootstrapping. Basically, suppose you are having a bag, and in bag there are 50 numbers like 1, 7, 6. So these are the random numbers. So you pick any 5 numbers first, note it down this, and keep the numbers back to the bag. Again, you note it. Again, you draw 5 numbers, note it here. Keep the numbers back to the bag. Again, you pick 5 numbers. So this is called with replacement. Picking with replacement. Suppose you do 2000 times. Suppose you do 2000 times. So after 2000 times, your number of data is 10,000. Right? Initially, if your distribution is like this, but after bootstrapping, your distribution is like this. So distribution is changing from non-normal to the normal distribution. So this is the benefit of bootstrapping. So bootstrapping process makes your data normally distributed. So sometimes if somebody asks you that because your data is non-normal, not normal, how you going to apply parametric distribution, parametric test? So simplest answer is that I converted my non-normal data into a normal data by applying the bootstrap process. And after applying the bootstrap process, whatever the result I'm getting can be applicable on the population. So this is the simple answer you can give. So bootstrapping is one of the powerful method incorporated in PLS software. So I hope you understand what is the meaning of bootstrap process. Let me show you the bootstrap process. And if I type Google bootstrap process and show you the image. So there are many various terms or bootstrap plus normal distribution. Okay, so this picture I want to show you. Right. So before the bootstrap, the distribution is this. And after the bootstrap, the distribution is like this. So this is the advantage of bootstrapping, that your distribution initially, which was initially not normal, but after that, your distribution becomes normal. Right. Okay. So this is the advantage of bootstrap. So we were discussing. Okay. So let me take this picture. So it is from Wikipedia. But there are many pictures here. But I think this picture makes you more clarity that how the bootstrap changes the distribution of the data. So initially the data is not distributed, but after bootstrap process, the data will be normally distributed. Okay. So in most of the cases, the scholars ask me that how many times we should run bootstrapping process. And the simplest answer is 500 to 2000. I have seen it is 2000 is mentioned in the paper. I have also seen 500 is mentioned in the paper. So any number between 500 to 2000, you can apply as a bootstrap process. So whenever you go for PLS, I'm showing you, suppose I am doing hypothesis testing. For hypothesis testing, I want a result that can be applied on the population. So you can go to the calculate bootstrap, and how many times you want to do bootstrap, you have to mention here, like 500, 600, 2000, like so 2000. So if I run the model after doing 2000 samples in bootstrapping, I'm telling you I'm getting the results which is better than the without bootstrap results. So bootstrapping is the method which can give you better results. So I hope you understand the bootstrapping. There are two types of bootstrapping in the software: basic bootstrapping and complete bootstrapping. So we will discuss this in hypothesis testing. So what is the difference between basic bootstrapping and complete bootstrapping? So bootstrapping is one of the important feature is in PLS software, which you should understand. The next and the last concept is goodness of it. The problem is that in PLS, we don't have most of the goodness of it. In MOS, we are having very large number of goodness of it. We are having CFI, GFI, AGFI, CFI, NFI, so many things. But in PLS software, the definition of goodness of it is totally different. In one of the paper, that's why I put the cut and paste the concept. In one of the paper, I found that the goodness of it in PLS software is measured by this formula. So goodness of it you can calculate by multiplying underscore root AV multiplied by the R square of the dependent variable, right? So because R square, you know that R square is always calculated for the dependent variable, and square root of AV, if you multiply, so if this value is coming 0.10, it is very small, 0.25 median, and 0.36 is good. So any value which is coming more than 0.36 GOF, goodness of it, then it is considered to be good. Otherwise, the software gives you the goodness of it in case of measurement model. If I go to calculate consistent PLS, this, the software also give you the sum of the goodness of it, not in large number, but small number. You can see the last value, model fit. If you go to the model fit, two things you have to see: SRMR and NFI. And the criteria is the SRMR should be less than 0.08. In some of the papers, they mention 0.05. And NFI, in some papers, I have seen it should be greater than 0.8. In some papers, they quote 0.09. So SRMR less than 0.05 is excellent. 0.08 is satisfactory. NFI more than 0.8 is satisfactory. NFI more than 0.9 is excellent. So this measure fit you can also report in the paper. So we have to show in the slide also. In this slide, you will get these values, and these are the criteria. SRMR less than 0.5, NFI more than 0.9 is excellent, otherwise 0.808, and 0.8 is the satisfied criteria. So I think that's it for today, and we have discussed almost the different type of assumptions we have to check about the scale. What do you mean by scale? I hope you understand now. And whenever you are collecting data from the questionnaire, you have to check all these things, report it in the paper, and once all the conditions are fulfilled, then you can go for the hypothesis testing. So that's why the today's session is only focusing on the assumption part. These are the different assumptions we have to prove, you have to show in the paper, and then only you can go for advanced hypothesis testing. So I hope we have understand all the basic concepts. I tried my best in explanation. And now if there is any query, we are going to discuss. So give me a minute so that I can stop recording and unmute you all. Meanwhile, if you can raise your hand, I will ask one by one.